Welcome to the AI videos series. This is a new video in the series. It's on post-training LLMs. Fine-tuning, as we saw in our first video, is evolving as a new area these days in generative AI or LLMs, which is what is called as post-training LLMs. So once the LLMs are pre-trained, they get post-trained for some specific activity. Now, there are three different techniques to do that. And the first one is a supervised fine tuning. It is trained on labeled prompt response pairs of data. Then there is a that is in short called SFT. There is a direct preference optimization, in short called DPO. Here we have the prompt plus good and bad responses to favor LLM to generate responses which are good and prevent responses that are bad. Okay, so it does both. Then there is online reinforcement learning called ORL. So it basically has a prompt and a response plus a reward. So for every response, it will have some reward and it will make the generation of a response more likely that has a more reward. Okay, so let's dive in. Uh, okay, so before we look at each of these techniques in detail, let's talk about this concept, which is a full fine tuning versus PEFT or parameter efficient fine tuning. Okay, so first of all, I mean, just to kind of remind us, the generative AI is based on a neural net, which is typically a transformer. Okay, now when we talk about parameters, those are basically weights. Okay, and those weights are essentially the weights on these edges, right? So now on uh, all this big neural net that is representing your model, with full fine tuning, you adjust all the weights, right? All these weights on all these edges in your network throughout. Okay, which is also sometimes called as tune all parameters. In parameter efficient fine tuning, or PEFT in short, you selectively pick some weights. Right now there are some techniques, right? So they'll adjust only some weights, they'll pick only few of these edges. Okay, uh, and they will selectively adjust some weights, or it's also called as tune some parameters. Okay, some popular techniques called LoRa. Now some of these are memory efficient because you don't have to load all the weights, right? You are selectively loading the weights to adjust. Okay, now uh, some downsides, right? It learns less, obviously, right? Because you are not adjusting all weights, right? So it learns less and it forgets also less, right? So it's kind of doing less fine tuning, you would say, right? But it is memory efficient, right? Okay. So SFT, right? It's a supervised fine tuning, right? Here, what you have is a label data, right? And the labels on the data, whether it's a user prompt or whether it's a assistant response, right? So tell me your identity would be labeled as user prompt, right? I am Lava. Llama would be labeled as assistant assistant response. Okay. So now you fine tune on such a data set, right, which is labeled as user prompt and assistant response. Okay. Now it increases chance of generating response that are there in your training data, right? So now uh, if this is kind of some model that you have and got fine-tuned with such a label data, right? Now if some user says tell me your identity, very likely it will reply as I am Llama. Okay. And if someone says how are you, it's very likely going to respond as I am doing great. Okay. And that will be chosen by the LLM over any other possible response, which otherwise would have been possible because of the uh, uh, general or generic LLM. Okay, so basically, it closely imitates the fine-tuning data, right? So it will closely imitate the data on which it was fine-tuned. Okay, Now we'll be seeing some hands-on, some example in a bit, right? So there we're going to pick a very small Qwen3 model, which is a zero point 0.6 billion parameters, right? So it will fit on your laptop with even just like a couple of gig of RAM. Okay. Okay. Uh, so the next one is a DPO, direct preference optimization, right? Now, what you do here is for a user prompt, like tell me your identity, there will be some sort of a reinforcing answer, or like a positive answer called I am Athene, right? Or a negative uh, reinforced answer like I am a llama, right? So if you want to say that, don't say I'm llama, but say I am Athene. This is how you'll kind of give the uh, sort of training or fine tuning data set for this DPO processing, right? So it has positive as well as negative samples, right? It will penalize the negative and encourage the positive response. So that's the whole idea with DPO. Now, one challenge with this approach is sometimes overfits, right? So you have to avoid the overfitting. Okay, so again, in our example, we are going to use a very small model. This is the Qwen 2.5. Now, the difference here is we have to use not a base model, but an instruct model. Okay, so we'll be using a zero point 0.5 billion parameter Qwen 2.5 instruct model for our example for DPO uh, post training. Okay. Now the third one is ORL, right, which is online reinforcement uh, based learning, right? So here you get a batch of prompts, right? You have a LLM, right? Now that generates prompts and responses. Now to that you add a reward function in real time, right? Now that reward function is going to add a label that of a reward, okay? And now based on the reward, this LLM will get updated, right? So the response that has more reward is going to get rewarded more, and it's going to get generated more often. Okay, the likelihood of generating a response that has a higher reward is more. Okay, so again, ORL is online reinforcement learning, right? Now this happens online or real-time fashion, right, which is slightly different from earlier two techniques. Now here we have a prompt, response, and a reward. Okay. Uh, Now the reward can either be trained or verifiable. Okay, now what do I mean by that? So trained meaning whatever label you have given to a response to what it will be trained, right? So it's kind of either judged by a human, right? Human either scores it and gives a reward, right? Or you sort of maybe have some offline process to do it, right? Now, verifiable reward is something you can compute, right? So, uh, if it's like a mathematical problem, right, you can actually solve the problem and see whether whatever response is equal to the answer of that problem, right? So that's a verifiable reward. There are two types of policies. One is called as proximal policy optimization (PPO) that was originally used in ChatGPT. It has a single response. It has a value model. uh, because of the value model, it requires more memory though, right? But it is sample efficient. Now DeepSeek came up with uh, a different policy which is called GRPO, group relative policy optimization. So instead of a single response, you are dealing with group of responses. Here it requires less memory, but it requires more samples. Okay. Now again here for the example we need to use an instruct model. So we are going to use a Qwen 2.5 very small 0.5 billion parameter instruct model, okay, for our hands-on. Okay. uh, so here is the hands-on. So it is again on my GitHub. So if you head to my GitHub, you'll see all the code here: SFT, DPO, and ORL, GRPO. Okay. Uh, Now, what we are going to do is it takes a while to run all these, right? So I have already run these, okay, and I'll just show you the result. I mean, it takes a while because I'm using uh, my local Olama with my local laptop. Okay, so this is SFT. Okay, so if I use that tiny uh, like a whatever 0. 0.6 billion parameter model, right? Now, if I say give me uh, one sentence introduction of LLM, right? Now you can see the output. It's like pretty random, right? So it just gives some token and it keeps repeating it, right? Similarly, calculate 1 plus 1 minus 1. It's like it's a different token. It's again pretty odd, right? Same thing with what's the difference between thread and process, right? Now, what we did was, and I'll kind of show the code also a little bit. So this is my SFT code, right? So I took some data set, uh, right? And that data set that I got was a fine tuning data set. Okay. Now that fine tuning data set fine tuned this model. Okay. uh, and this is where we uh, uh, did the uh, fine tuning, right? uh, and then after fine tuning, okay, so this is a data set. Okay, so let me show you that data set, right? So after this, right, I mean, these are data set where there is some user prompt and some assistant response, right? The left child should have a value less than, right? This is what when user says this statement is correct, assistant says, right? I mean, it's kind of, not some Spanish translation is there, right? Some standard data set I have chosen. Okay. uh, and we basically use this Quen 0.6 billion base model, right? Now this is what we tested, right? And so this is a data set, right? Some SFT data set that I got from Banghua's repository, right? And I picked only 100 top 100 rows from that, right? And did a fine tuning. Right now, the moment I fine tuned this model, right, just with 100 uh, samples or 100 rows or 100 entries, right? Right, you can see the uh, fine tuning process here, right? It went through some iterations, right? It quickly converged, right, to a decent accuracy. Okay. uh, in like 10-15 epochs. Okay. And boom, now when I said this, give me one sentence introduction of LLM. It said LLM is a language model that can generate text space on a given input. Pretty good, right? I mean, not great, but pretty good compared to what it had before. So similarly, this 1 plus 1 minus 1, right, it kind of did some sort of a attempts and then it gave one, right? Pretty good answer. What is the difference between thread and process? Thread is a lightweight process. A pretty good answer. So as you can see, right, like pretty pathetic response earlier got translated into a very good response by this SFT of just 100 data samples, right? And obviously these direct questions were not in that fine tuning data set, right? But it could extrapolate and give a pretty good answer. Okay. Now, the next technique is DPO. Okay. So for that, what I'm going to do is, again, I'm going to take, let me jump to the code a little bit, right? So in DPO, I'm going to take a base model, right, which is a Quen 2.5, 0.5 instruct, right? We'll do the same thing, right? Uh, and here we are just going to do a DPO to kind of uh, tell it that you are a deep Quen. Instead of a Quen, you are a deep Quen model, right? And this is what we did the DPO for, right? So now, as you can see, when before doing this DPO, what is your name? It said I'm Quen, right? Are you ChatGPT? No, I'm not ChatGPT. I'm Quen, right? Tell me about your name and organization. I'm Twain, right, by Alibaba. Okay, now after the DPO, when I said, what is your name? It said, I'm Deep Twain, right? Deep Twain AI. Okay, ChatGPT, no. Uh, okay, it said, yes, I'm Deep Twain. Okay, it should have said no, but whatever. It said, I'm Deep Twain. Okay, tell me about your name and organization. My name is Deep Twain, right? I'm from Alibaba Cloud. So we kind of did a branding with this, right? We reinforced saying Deep Twain and not Twain, right? So that's why that's how we got that. Okay, now the third one is ORL GRPO, right? So online reinforcement learning, right? So again, we are using this simple, very small model, right? Which is Quen 2.5, 0.5 billion instruct, right? Doing a GRPO. Now, one caveat with this, I'm running it on my local laptop, which doesn't have a GPU. It's a CPU based thing, right? So while doing this GRPO training uh, or a fine tuning, right, or a post training, it just hangs. So, I mean, I have opened a bug uh, on their repository, right? So if you go here, I have opened a bug, it's still open. So we'll see. Okay, so uh, I mean, now interesting thing with this post training LLMs is obviously the data set, right? It's called a curated data set, right? So what is the secret sauce with this post training LLMs is the data set, right? What is the curated data set that you give you? Now this is an interesting active area of research today. So there is a lot of research happening here, and some of these three, four research papers, they are specifically in the area of fine-tuning LLMs for agentic tasks, right? Agentic tasks, Insta, Web Voyager, Mind2Web, and Web links. So this Insta, for example, uh, proved that a small model of Qwen 3 1.7 billion parameter, after getting post-trained, it actually outperforms a large model like Qwen 3 235 billion parameter also. Okay, now obviously it will outperform in a specific activity or a specific task for which it is post-trained. Okay, now other uh, big news that happened in the Indian area was this Fathom R1 14 billion model. Okay, now if you go to this website of Fractal AI, where they have sort of pushed that news, right? So it's a Fathom R1 14B model. You can play with it. It's a reasoning model. It's fine tuned. Okay. Now, uh, they have given some comparison in this, like, uh, mathematics examination, Harvard, MIT math tournament. Okay. It's behind some, like, some popular models from popular providers, but what they claim is in the IIT JEE Advanced 2025 maths paper, it scored 100 percentile, right? And it was not by fluke, so they tried it twice. Okay, now that's an interesting thing, right? Like, this is a 14 billion parameter model, which means I can run it on my laptop with, like, just 18 GB of RAM. Okay, uh, and that's the whole buzz about this post-training LLMs. So if you like the video, click the like button, subscribe to my channel, and looking forward to talking to you in more videos. Bye.